and surface geology measurements. And it did that with three, but it only observed a portion of that surface, as Alan mentioned. But I'm delighted to say that with NASA's MESSENGER mission, we're not only going back to Mercury, but we're going back to stay. MESSENGER is one of those PI Discovery class missions designed to be a very comprehensive set of measurements of Mercury. It is a hard planet to get to. It's remarkable that on a discovery budget, we've been able to end up passing by Mercury, as I mentioned, for a very long time. And now, with several flybys, we're going to be able to finally get into orbit in 2011. Now, MESSENGER's prime mission will be for 1 Earth year. That's 365 days. It turns out that's 4 Mercury years or 2 Mercury solar days. So let me now turn it over to Sean Solomon to tell us how MESSENGER saw Mercury on that first encounter earlier this month. Sean?
Thank you, Jim. As Jim said, as Alan said before him, it's been a long wait for all of us in the planetary science community to go back to Mercury. To put it in the context of today's headlines, when Mariner 10 last flew by Mercury, the man in the White House was Gerald Ford. And we're just delighted to be seeing the first new data close up from the planet Mercury in nearly 33 years. That data came from a flyby that began 2.5 weeks ago, and it began with the approach to the planet that you see on the monitors. And as we approached, the suspense built. As we flew by and gathered data from all the 7 science instruments on the MESSENGER payload, we were continually surprised. It was not the planet we expected. It was not the moon. It was a very dynamic place with things changing very rapidly. Features that we saw with the MESSENGER camera that you'll see later today haven't been seen on any other planet. My colleagues to my left are going to talk about some new images. They're going to talk about the altimetry that we measured on closest approach. And I want to spend just a couple of minutes talking about the planet's magnetosphere, the planet's atmosphere, and a little bit about the planet's surface. And I want to leave you with the message that all of those aspects of the planet Mercury are closely interlinked. It's a very dynamic planet with an awful lot going on. But let me start with the magnetosphere. The Earth, of course, has a magnetic field. The Earth has a magnetosphere, and we owe our lives to this magnetosphere. It is a protective bubble around our planet that keeps cosmic rays and energetic particles from the sun from impacting the surface and doing genetic damage to anything living here on the Earth. But we know that the Earth's magnetic field changes. We know that there's space weather that modifies our magnetosphere. The only other example in our solar system of an Earth-like magnetosphere and magnetic field is tiny Mercury. If we could have the animation, you'll see some measurements that were made as the spacecraft flew through Mercury's magnetosphere. A novel instrument from the University of Michigan called the Fast Imaging Plasma Spectrometer measured for the first time at Mercury some low-energy plasmas that you see on the top plot, mostly of solar wind origin, and some heavier ions in the lower plot that are species derived from Mercury's atmosphere or surface. These are telling us that this tiny magnetosphere is full of hot plasma, some of it from the sun, some of it from processes interacting with the surface in the atmosphere. And it's a wonderful treasure trove of information that will allow us to link to other aspects of the planet. You get a nice view of our flyby, the fact that we crossed the major boundaries of the magnetosphere, and that we spent a lot of time sampling the environment of Mercury. The next slide shows us what we measured with the magnetometer at the same time. Again, the magnetometer showed us that we were crossing the principal boundaries of the magnetosphere. We could identify them on the basis of models of the planet and Mariner 10 observations. You see in the center of that plot the strong magnetic field recorded from the planet itself. It's not as strong as the Earth's field, but it was very well recorded, allowed us to learn something about the geometry of that field. But we saw also the plasma boundaries that were very consistent with what we saw with the plasma instrument. We had an instrument on this spacecraft to measure energetic particles at Mercury, but none were seen. The energetic particle spectrometer did not see any signals at Mercury, which was a bit of a surprise because Mariner 10 did record such observations. And we think that's telling us that the magnetosphere of Mercury is very changeable, that it's a function of the activity of the sun. We went by at a particularly quiet time in solar activity, and it can change on matters of seconds or minutes or hours. To prove that, we'll have to wait for some of the future observations we make during flybys. Let me turn next to the next graphic, which summarizes very simply some of the things we learned about Mercury's internal field. Recall that Mars does not have a global magnetic field. Venus does not have a global magnetic field. Among the inner planets, only Mercury has a magnetic field like the Earth, albeit smaller in magnitude. And these are some of the basic questions we asked of the observations we took as we flew by Mercury. Does Mercury's field look dipolar, meaning does it have a north pole and a south pole, as if a bar magnet were at the center of the planet? And the answer seems to be yes. Like the Earth's field, Mercury's field is dipolar. It may arise by similar processes, but that's a question we're going to need more data to solve. But it looks dipolar. In fact, it's tilted with respect to the spin axis by an amount not very different from that for the Earth's field. Has the field changed since Mariner 10 in the last 33 years? The Earth's field does change in modest ways over that time scale. We can't tell yet for Mercury, but we'll be looking to see a signature of that change because that is the telltale sign of the mechanism of formation of the field. And finally, are there magnetized patches in the crust of Mercury? That was one of the big surprises that Mars Global Surveyor showed us at Mars, that Mars, although it doesn't have a global field, has strongly magnetized regions of crust left over from a global field billions of years ago. To a lesser degree, the Moon and Earth have magnetized patches of crust. We didn't see such a patch on Mercury at this flyby, but it's something we're going to be looking for in future flybys and in the orbital phase. Let me turn to Mercury's exosphere. Its very tenuous atmosphere, so tenuous that the molecules don't even collide with one another. The next graphic shows a view we took of the tail region of Mercury, looking at a wavelength that's particularly sensitive to neutral sodium, which is a species that shows up very well spectrally. This is the highest resolution image ever taken of Mercury's sodium tail, which points in the direction opposite to the sun and is a major process for removing material from Mercury's exosphere and sending it off into space. These are highly energized atoms of sodium that have come from the atmosphere, have come perhaps from the surface, and are now streaming away from Mercury. You see from the color scale that there's an asymmetry north to south, that the sodium tail is much stronger in the northern part of the planet than in the southern part. And that has been seen from Earth, but we have some new observations that cast some light on why that might be so. The next slide shows measurements taken of the tail in an ultraviolet wavelength. If we could have the next graphic. There it is. Sensitive to hydrogen, neutral hydrogen. And there you see also this north-south asymmetry, with the northern hemisphere being much more enriched in hydrogen, at least with respect to our viewing geometry, than the southern hemisphere. Hydrogen, we believe, is mostly of solar wind origin, and the fact that this asymmetry is seen in hydrogen points to some mechanism that involves an interaction between the solar wind and the magnetosphere. The fact that the hydrogen and sodium being a much heavier component of the atmosphere, have the same asymmetry suggests that there's at least a strong contribution of the same solar wind magnetosphere interactions in the sodium loss, at least at the time we're flying by. So we're chasing some basic questions that have been with us for 20 or 30 years. How does Mercury derive its atmosphere, because it's very short-lived? How are the species in the atmosphere lost? The tail is just one of these mechanisms. And having a variety of species